we shall be able to know what is the principle of spectroscopy and the various common spectroscopic techniques you shall be made familiar with, and we shall be focusing on UV visible spectroscopy, IR spectroscopy, neutron activation analysis and mass spectroscopy. After studying this module, you shall be able to know what does the term spectroscopy actually mean and its principle behind the spectroscopic technique and the various spectroscopic techniques which are employed in forensic analysis. And especially the spectroscopic techniques become important when the amount of material which needs to be analyzed is very, very small, and that is why it becomes very important from a forensic point of view, because from the crime scene you will be getting some minute amount of evidence, the trace evidence, which can be easily identified by these spectroscopic techniques. So, before you analyze these samples and evidence in the lab as forensic scientists, it is very important for you to understand the chemistry behind this spectroscopic technique. The study of interaction of matter and radiated energy is what we mean by spectroscopy. If we talk about history, in history the technique of spectroscopy originated from the study of dispersion of visible light with the help of prism in accordance with its wavelength, and this technique you are familiar that how prism will make the visible light deviate into so many different light depending upon their wavelength, like a Vidya-mitra pattern. After this, the theory related to spectroscopy was expanded that consisted of the interaction with radiant energy and as the function of its frequency and wavelength. The data obtained from spectroscopic analysis is then represented by the plot of function of frequency and wavelength in relation to the response of interest, and this plot is very commonly called as spectrum. If we look at the principle of spectroscopy, although there are a number of spectroscopic techniques, each based on different basic principle, but a typical spectrophotometer is said to consist of a light source that provides light which has to be of a known wavelength, a holder to position the sample which may be solid, liquid or gaseous, and a system of lenses and photocells that compare light shining on the sample with the light passing through. So, that difference is compared and finally that is put up on the plot as the spectrum. The presence of components which absorb light at that wavelength is shown when there is a decrease in the intensity of light passing through that substance. Obviously, when you have a solvent, when there is no substance, then the light, if it is passing with one particular intensity, then the moment you add something, the intensity is going to decrease. And this absorbance parameter is quantitative in nature, that is, it can be measured to a very precise amount and is a measure of the concentration of material, and the wavelengths of maximum absorbance are characteristic of the type of material. A few common spectroscopic techniques which are very commonly employed in the forensic analysis, they are UV visible spectroscopy, IR spectroscopy, neutron activation analysis, and mass spectroscopy. So, dear students, with this background of spectroscopy in general, let us go into each of them one by one and see how they vary, keeping this broader principle as the background. So, let us begin with going into this detail with the help of graphics and visuals.
UV visible spectroscopy. In this type, the spectrum consists of photon energies in the range of 36 to 72 kilocalories per mole in the visible region, and in case of near ultraviolet, this energy ranges up to 143 kilocalories per mole. The energies are adequate to move or excite an electron to a higher energy state. Subsequently, absorption spectroscopy passed out in this region is at times referred to as electronic spectroscopy. A number of electronic excitation which can take place in organic molecules has been discussed. Principle. In general, energetically favored electron promotion will be from the highest occupied molecular orbital to the lowest unoccupied molecular orbital, and the resulting species is called an excited state. Once sample molecules are exposed to light having an energy that matches a possible electronic transition within the molecule, some of the light energy will be absorbed as the electron is promoted to a higher energy orbital. The wavelength and degree of absorption is recorded by an optical spectrometer. In addition to this, there are certain functional groups that accelerate light absorption. Such absorbing groups are referred to as chromophores. A list of some simple chromophores and their light absorption characteristics is as follows. As shown, the various chromophores, their examples, excitation, and lambda max has been shown in this table. The presence of chromophores in a molecule is best documented by UV visible spectroscopy, but the failure of most instruments to provide absorption data for wavelengths below 200 nanometers makes the detection of isolated chromophores problematic. By chance, conjugation usually transfers the absorption maxima to longer wavelengths. The various terminology for absorption shifts are: to longer wavelength, the descriptive term used is bathochromic. To shorter wavelength, the term used is hypsochromic. To greater absorbance, hyperchromic is the term. To lower absorbance, the descriptive term is hypochromic. Next, we move on to instrumentation and working. A ray of light emanating from a visible ultraviolet light source is divided into its component wavelengths with the help of prism or diffraction grating. Each monochromatic beam is then further divided into two beams of equal intensities by the help of a half mirrored device. A sample ray of light is passed through a transparent container having a solution of the compound in a transparent solution that is to be studied. The second beam of light is the reference beam that is passed through a transparent container having only the solvent. Electrical detectors measure the beam intensities, which are then compared. The intensity of the reference beam is referred to as I naught, that suffers slight or no light absorption. The intensity of the sample beam is defined as I. In a short span, the spectrometer scans the component wavelengths. The visible region scanned is usually in the region of 400 to 800 nanometers, whereas for the UV region it is 200 to 400 nanometers. If the sample compound does not absorb light of a given wavelength, then I is equals to I naught. On the other hand, if the sample captivates light, then I is less than I naught, and this difference may be plotted on a graph. Absorption may be presented as transmittance or absorbance. If no absorption has occurred, then T is equals to 1 and A is equals to 0. Most spectrometers show absorbance on the vertical axis, and the normally detected range is from 0, that is 100% transmittance, to 2, that is 1% transmittance. Lambda max is denoted as the wavelength for maximum absorbance. Various components exhibit different absorbance and distinct absorption maxima. Next, we will study about the applications. UV visible spectrometer has a significant part in analysis of numerous compounds, metals, etc. Its use is readily understood from depth of its applications. It is also used in fields of forensic investigations, food and agriculture, biological and clinical chemistry, environmental chemistry, pharmaceuticals, etc. Now we will study about IR spectroscopy. Infrared radiation does not have adequate energy to make electronic transitions, as is the case with ultraviolet radiations. Absorption of IR is limited to complexes having small energy differences in the probable vibrational and rotational states. The rotations and vibrations taking place in a molecule must result in the net change in the dipole moment so that the molecule can absorb infrared radiation. The alternating electrical field of radiation interrelates with fluctuations in the dipole moment of the molecule. The radiation is absorbed when the radiation frequency matches with that of the vibrational frequency of the molecule, thereby resulting in a change in the amplitude of molecular vibration. Molecular vibrations. The positions of atoms in a molecule are not fixed. They are subjected to an amount of various vibrations. Molecular vibrations come under two different classes of stretching and bending. First is stretching. Change in interatomic distance along bond axis. It is of two types. First is symmetrical and asymmetrical. Next, we move on to bending. Bending is change in angle between two bonds. Four kinds of bending are present: rocking, twisting, wagging, and scissoring. Vibration coupling. In addition to the vibrations discussed, interaction between vibrations takes place, that is, coupling, if the vibrating bonds are joined to a single central atom. Now we move on to instrumentation. First is IR radiation sources. Infrared apparatuses involve a source of radiant energy that emits infrared radiation that should be steady, strong enough to be detected, and can spread over the preferred wavelength. A number of sources of infrared radiations are incandescent lamp, tungsten lamp, Nernst glower, and lastly, mercury arc. Now we move on to sample cells and sampling of substances. IR spectroscopy has been used for the characterization of solid, liquid, or gas samples. First is solid. Various techniques are used for preparing solid samples, such as solid run in solution, solid films, mule technique, pressed pellet technique, etc. Liquid samples are kept in the cells made of alkali halides. Aqueous solvents are not used because they will dissolve the alkali halides in the cell, and hence only organic solvents like chloroform are used. Next is gas. Sampling of gas is analogous to the sampling of liquids. Monochromators. Various types of monochromators are prism, gratings, and filters. Prisms are usually prepared of cesium iodide or sodium chloride. The filters are of lithium fluoride, and diffraction gratings are formed of alkali halides. Next, we move on to detectors. Detectors like thermocouples, bolometers, etc., are used to measure the intensity of unabsorbed IR radiation. Next are the applications. Infrared has been used to measure blood alcohol content, to analyze drug, fiber, and pain samples, and to visualize wounds such as bruises or bite marks on tissue. It also has been used to detect blood and explosives. Neutron activation analysis. Neutron activation analysis, or NAA, is a nuclear process used for defining the concentrations of elements in a huge amount of materials. It permits distinct sampling of elements as it neglects the chemical form of a sample and emphasis exclusively on its nucleus. Neutron activation analysis was found in the year 1936 by FSC and Levi, who established that samples comprising of certain rare earth elements turned out to be highly radioactive after being exposed to a source of neutrons. This observation resulted in the use of induced radioactivity for the identification of elements. Principle: the sample is bombarded with neutrons, causing the elements to form radioactive isotopes. The radioactive emissions and radioactive decay paths for each element are well known. By using this information, the spectra of emissions of radioactive sample are studied, and the concentrations of the elements are determined inside it. Now we move on to instrumentation and working. NAA is significantly different from other spectroscopic analytical techniques as it is not based on electronic transitions but on nuclear transitions. To perform the neutron activation analysis, the sample is put into an appropriate irradiation facility and bombarded with neutrons. The result is that artificial radioisotopes of the elements are formed. After being irradiated with, the radioisotopes decay, emitting particles, especially gamma rays, which are typical of the element. For the analysis to be effective, the specimen or sample must be carefully chosen. NAA can perform non-destructive analysis on solids, liquids, suspensions, and gases with no or minimal preparation. Also, this procedure can be employed on objects that are irradiated and can be analyzed without the sampling being done. About 50 milligrams is a sufficient sample. The sample is put into a quartz or polyethylene vial. Neutron flux is defined as the constant at which the sample and standard are packed and irradiated in a suitable reactor. A typical NAA reactor employs uranium fission, thereby giving a high neutron flux and the maximum accessible sensitivities for a number of elements. The neutron flux of a neutron activation analysis is in the range of 10 to the power 12 neutrons per centimeter square per second. The neutrons produced are generally of comparatively lower kinetic energy of the order of 0.5 electron volts. The neutrons of low kinetic energy are also known as thermal neutrons. On being irradiated, a thermal neutron relates with the target nucleus through a non-elastic collision, causing neutron capture. A compound nucleus is formed due to this collision, wherein it is in an excited state. When the target nucleus binds with the thermal neutron, it results in the formation of the excitation energy of the compound nucleus due to this binding. This excited state is unfavorable and the compound nucleus will almost instantaneously de-excite into a more stable configuration through the emission of particles and one or more characteristic prompt gamma photons. By the emission of particles and delayed gamma photons, there is a decay in the newly formed radioactive nucleus. The starting de-excitation process is much faster than the decay process, which is comparatively slower. and relies on the typical half-life of the radioactive nucleus. After being radiated, the sample is left for a definite decay period and put into the detector that measures the nuclear decay in accordance with the emitted particles or the emitted gamma rays. Next is the neutron sources, a nuclear reactor and a DT fusion reaction in a gas discharge tube. Now moving on to detectors. Various detectors are used in neutron activation analysis. Most are designed to detect the emitted gamma radiation. Various types of gamma detectors used in this analysis are the gas ionization type, scintillation type, and the semiconductor type. Of these, the scintillation and semiconductor type are the most widely employed. The second type of detector employs a radiation sensitive crystal, most commonly thallium doped sodium iodide, that emits light when made to collide with gamma photons. All these detectors have resolution, sensitivity, and stability. Moving on to analytical capabilities. Neutron activation analysis can identify around 74 elements, depending upon the experimental procedure, with minimum detection limits ranging from zero point 0.1 to 1 into 10 to the power 6 nanograms per gram, depending on element under investigation. Applications. Neutron activation analysis is a sensitive multi-element analytical technique used for both qualitative and quantitative analysis of major, minor, trace, and rare elements. A specific advantage of this procedure is that it does not destroy the sample, and thus has been used for analysis of works of art and historical artifacts. Neutron activation analysis can also be applied to determine the activity of a radioactive sample. Neutron activation analysis has an extensive range of applications, comprising its use in areas of archaeology, pedology, geology, and in the semiconductor industry. The technique can also be applied to several forensic science problems, namely toxicology, detection of firearm residues, and investigation of the possibility of common origin for two samples. Accuracy of NAA is in the region of 5%, and relative precision is often better than 0.1%. Next, we move on to mass spectrometry. A mass spectrometer converts the individual molecules to ions so as to study the properties, and they may be moved about in the eternal magnetic and electric field. The three indispensable roles of a mass spectrophotometer and the related apparatuses are: first, in ion source, a small amount of the sample is generally converted to cation by loss of an electron. Second, in mass analyzer, normally the ions are separated according to their M by Z ratio. Lastly, the detector detects the separated ions to be analyzed, and the results are depicted on a chart. The formation and manipulation of ions are done in vacuum of an atmospheric pressure of 760 mmHg. As these ions are short-lived and are reactive, in a general technique, ionization is caused by a high energy beam of electrons, and ion separation is attained by increasing and focusing the ions in a beam that is made to bend by the external magnetic field. The ions are then detected electronically, and the resulting information is stored and analyzed in a computer. Instrumentation and working. The main component of the spectrometer is the ion source. Sample molecules are made to collide with electrons that are generated by a heated filament. This is called an electron impact source. Gases and volatile liquid samples are allowed to leak into the ion source from a reservoir. Non-volatile solids and liquids may be introduced directly. Cations formed by the electron bombardment are stripped away by a charged repeller plate, which attracts the ions and accelerates them towards other electrodes, consisting of slits by which the ions pass in form of a ray. Some of these ions fragment out into smaller cation and neutral fragments. A perpendicular magnetic field deflects the ion beam in an arc whose radius is inversely proportional to the mass of each ion. Lighter ions are deflected more than heavier ions. By changing the power of the magnetic field, ions of varying mass can be focused gradually on a detector secured at the end of a curved tube. When a high energy electron strikes a molecule, it often ionizes it by colliding away one of the electrons of the molecule, which may be bonding or non-bonding. This leaves behind a molecular ion. Residual energy from the collision will result in the molecular ion to break into neutral pieces and smaller fragment ions. Depending on the nature of neutral fragments, these fragmented ions can either be carbocations or radical cations. Next, nature of a spectra. The spectra is generally shown by a vertical bar graph, wherein each bar denotes an ion having a particular mass to charge ratio, and the length of the bar specifies the relative quantity of the ion. Base peak is defined as the most intense ion having an abundance of 100. The ions so created by this procedure consist of a single charge, such that the mass to charge value is equal to mass itself. The highest mass ion in spectra is typically thought to be a molecular ion, and the lower mass ions are fragments from the molecular ion, supposing the sample is a single pure compound. Applications: to identify various compounds, the difficulty to study the fragmentation patterns has resulted in mass spectra being used as fingerprints. Environmental pollutants, pesticide residues on food, and controlled substance identification are a few examples of this application. In such analysis, a microgram or less amount of the sample may also be taken.
Summary. Dear students, let us summarize what we have learnt in this module, which was focusing on spectroscopy. That is the spectroscopic techniques which will be useful to you as forensic scientists. We have studied that the study of matter and radiated energy is known as spectroscopy. We also learnt that when a light is made to pass through a substance, there is a decrease in the intensity of the light which is passing through the substance, and this indicates the presence of materials which absorb light at that wavelength. The absorpance is quantitative and it is a measure of the concentration of the material, and the wavelengths of maximum absorbance are also characteristic of the type of material. And knowing this and comparing the known spectra, you can identify whether it is the same compound or not. A few common spectroscopic techniques that are employed in forensic analysis are UV visible spectroscopy, the IR spectroscopy, neutron activation analysis, and mass spectroscopy. We also learnt that in UV visible spectroscopy, if sample is introduced to the light comprising energy that suits a probable electronic shift within the molecule, some of the light energy will be absorbed as the electron is promoted from a lower to a higher energy state. An optical spectrophotometer registers the wavelength at which the absorption takes place along with the degree of absorption of each wavelength. So, in UV visible spectroscopy, the electronic shift is very important, which is happening in the structure of these molecules, which are responsible, and you will be able to take the UV visible spectroscopy of these compounds. Only those compounds having small energy differences in the rotational and vibration states will absorb the IR radiation. So, that is what is important for the IR spectroscopy. We also studied about the neutron activation analysis, and in the neutron activation analysis, the sample is bombarded with neutrons, resulting in the elements to form radioactive isotopes. The radioactive emissions and the radioactive decay paths for each elements are well known, and this information is used to study the emission spectra of the radioactive sample, thereby determining the concentration of the elements in it. And coming to the mass spectroscopy, in order to examine the features of individual molecules, a mass spectrophotometer changes them to ions so that they can be moved about and influenced by external electric and magnetic field. So, this module, dear students, has given you idea about the spectroscopic techniques, and it is not that only one spectroscopic technique is useful. Most of the time it is multiple, and that will be giving you different clue about the structure of the molecule which is there in the sample that you have collected from the scene of crime, and that will help you analyze what was the compound which was there, and then you can better solve the case.